Hello. Right. So this is a kind of tutorial, kind of me just skimming through me learning my first experience with LLVM. And so this is inspired by, I think there was a similar talk last year about just how to write a backend in general. This extends this in the specific case of adding an assembler to your backend, and specifically focuses on some of the details you might trip up on if you just, like me, just start going, oh, TableGen is awesome, we'll get it to do everything for me. And then you start finding errors in your backend. As I said, I'm skimming over some of the details. I did write last year this nice 16-page document detailing every line of code you'll ever need to know. And as long as nobody has completely rewritten TableGen and the machine code framework by the time this finishes, then hopefully that'll still be up to date. If you don't necessarily have to write down that link, if you just look in the LLVM tutorial section, you'll find a link to it. And the code yet isn't in the main trunk, so yes, you can just, if you search OpenRisk LLVM, you will find this. So the big question is, why would you bother with this when, assuming you've already got everything working, you've probably spent time in probably bin utils, writing a nice assembler? Well, generally you run your compiler and LLVM or whatever will spend a nice amount of time carefully formatting the absolute perfect assembly file just for something else to parse it, which is probably a bit inefficient because, well, we already have the information. Why spend all this time just outputting it to read it back? And additionally, we've already defined our instruction set in our LLVM backend. Why do we want to do that all over again? So why not use the same definition that we previously had? Now, I'm talking about four main components which you probably want to add if you want to do assembly in your backend. Parsing instructions, which is mainly for, well, in my experience, mainly just for testing that stuff works. I mean, if you can't parse instructions, then you can't, well, if you want to check that you can encode them correctly, then you'll probably need a way of telling it, this is what I want to encode. Once you've done that, you'll probably want to be able to encode them, and while we're at it, why not decode them as well? And then at the end, you'll want to output an object file, which you can link using your favorite linker of choice. In the case of OpenRisk, as with many things, we're using elf object files, but nothing really here is specific to any particular object. Right, well, first you need to add, what you need to do is check that you've got everything that you need in your instruction definition so that TableGen can get you 95% of the way there, and then you can add all the corner cases. Now, in your instruction definition, there is this field, bits, which unsurprisingly stores your encoding. So what you will first need to make sure that you have is for all the instructions you will want to encode and decode that you've told the definition, this is what my opcodes are. Now, as a reduced down example, we have the instruction thing here, which sets the first 2 bits is one field, and standard thing if you've done any messing around with defining instructions in your backend, that is then defined later on, and then eventually you can probably get down to a nice definition that goes, my add instruction has this opcode, and unsurprisingly, your add instruction adds 2 values together. Now, the first stage is in parsing them, which turns a nice string like add R1, R1, R1 into a representation that can then be used internally. Now this is done in the class architecture name ASM parser, which uses information generated by TableGen to generate a list of operands which are then stored in the instruction with a general flow of is it this type of operand? If so, create it. If not, try something else or return 0 to say something's gone wrong. To assist with that, we need a structure which is called arc operand, which stores the information you'll probably want to know, such as this operand is a register and it is the second register. Now, one of the issues which I believe it's just a case if you have a full stop in your instruction name, like OpenRisk's add instruction is called l.add, and in order for this to be parsed correctly by the table generated functions, you will need to manually split up that string so that you add two initial operands, first L and then .add. If you have more complex things with, like, say L.add.float, then obviously you would need more operands. And for testing these, these is simply a case of write a nice assembly file with every possible instruction in your backend, and if you want to do this quickly, assemble it with, there's a command LLVM MC which will give you a nice output for this is what I've parsed, and basically create a test file that accepts as the correct input what is generated, assuming you've got it right in the first place. Otherwise, it becomes really fun to debug later when you're going, I thought I had all this right. For encoding is a similar case. You create a class MC code emitter, which calls for each instruction you want to encode, get binary code for insta, which in turn calls a bunch of functions that you have to encode. Specifically, get machine op value, which, while TableGen will be nice and will put together all of your fields, like say you have two registers that will nicely shift everything and or all your bits into whatever size bit field you want, you have to do the job of making sure that that your registers are encoded the correct way. And that, for example, say you have an 11-bit field for immediates, that you truncate that value yourself. TableGen does generate, I believe, a function to encode registers for you based on each register class, based on the assumption that the first register in your register class is encoded as 0, the next 1, etc. In the case where it isn't, you're therefore expected to create a nice function that is basically one nice long switch statement. Do I want to encode R0, return 0, R1, etc. Now, depending on your backend, you may have some specific operand types. For example, OpenRisk has a memory operand which consists of a register and then an offset from that register. And in the case of that, you're going to have to encode it yourself. Thankfully, again, TableGen will nicely piece together your encoding once you've given it a value. So, for example, with OpenRisk, there is a particular instruction which is, it's 16 bits for the register and immediate, but they're not all next to each other. There's some field in the middle. You don't have to worry about that. All you have to worry about is, I've got this 16-bit field, let's fill it up. So you would take, for example, take your register and then shift it the number of bits you want and OR it with your immediate and return an encoding which is then put into your instruction. Now for testing these, the same LLVM MC can run the same thing for you and can basically, you put in every instruction you've got and by hand assemble them and then check that the output is correct, and all being well it is. In the case of decoding, that's a relatively trivial matter once you've done the encoding, because essentially all the functions that you've written to do the encoding write a function to do the opposite. There is the added thing of, obviously you don't know where you may not necessarily know where an instruction starts and stops in the case of you having a architecture with, say, some 16-bit instruction and some 32-bit instructions. But in that case, all that you essentially need to do is, quite logically, you try the shortest instruction. Did that decode correctly? If not, we'll grab a bit more memory and see, is it this length instruction? And then carry on. And if you eventually go, it's not valid, we haven't got any instructions longer than what we've already read, then we'll start complaining. Now, all of the tables for doing this for you will be nicely generated, but you need to make sure that each possible bit pattern inputted is only uniquely mapped to one instruction. Because obviously otherwise, how are you going to know is it instruction A or B? And if you don't, when you try to compile, you'll have this nice little error here, which goes, wait, these two instructions here have the same encoding. You'll probably want to fix this. I'm not going to continue. Now, depending on what backend you look for inspiration to solve this, you will either find this nice essay-long comment in the Intel backend about how we resolve this, but in most cases, a nice quick way of resolving this in, for example, we have a return opcode which we have a return instruction in the backend which we never print out anyway. You can just mark this in your backend as that should be is code gen only, I believe, equals 1. Or in the case of instructions you've added just to make your life easier, is sudo. And then that means it won't evaluate this in the decoding tables. Finally, once you've encoded and decoded your instructions, you'll probably want to output this into a file. This involves making a few changes in certain places. You first have to define some fix-ups which represent values you don't know yet. Your backend will then try to go, oh, I know what this value is now. It will say you're looking at two functions. Okay, that function is over there. I can now replace this value I don't know. And you get nice good instructions. Otherwise, they get outputted as relocations, which then is the responsible of your linker afterwards to deal with. Now, most of this is done in the architecture-specific ASM backend class, which essentially has mainly three important functions that you need to worry about. The first being, well, I'll sort of describe these in a different order. A just fix-up value, which takes a value that you want to say, okay, this value that I want to put in this instruction, it formats it in a way that's now valid for the instruction. Then you want to apply it, which is done with apply fixup. And if you have to move things about and your code's going to run into some space where you have some space in your code where you just need to be able to execute stuff, the function write not data will, as the name suggests, will add to your output the encoding of a no operation so that when you go to run your program, you won't start throwing invalid instruction errors. And in the end, you create these two classes, create object writer and create foo. MC streamer, one instantiates the other. I can't remember off the top of my head which way round. And assuming that everything's working, you can now test your assembler, and if you're using Clang -integrated AS, I can't remember where in the Clang you set that as a default. And if everything works, you can be nice and happy. If not, comes the great fun of, I thought I put all these instruction encodings incorrectly. Now let's go by hand and reassemble everything and check that everything's right. That was a bit of a quicker talk through than I was expecting, but as I said at the beginning, if you want to know all the nitty-gritty details, there's a nice 16-page document you can find. If you just look in the LLVM tutorial section, you can find anything. Thank you.
What are the parsing limitations? So when you're parsing an instruction, what kind of syntax, how hard, what kind of instructions can be parsed and what kind of instructions cannot?
My experience with parsing is literally just the fundamental instructions, no.
So x86 ARM kind of instructions, right?
Yes.
What about the other kinds of assemblers that are more like a language?
I'm not in. I believe everything is generated kind of assumes like the type of input you normally. I'm not entirely sure off the top of my head how to describe it, but assembly.
Machine code.
Yes.
Yeah. What are you thinking? Something more high level than. Yes.
Mostly like a program. Mostly like a programming language, that has a syntax that can be described as BNF or some kind of that.
As I said, my experience with this is literally just, your standard instruction. Yes.
How about something of the complexity of IR could you solve? Something of the complexity maybe of IR that if it could kind of self-host.
I'm not sure. Again, what I should have said is, the last I really looked at this was about 6 months ago, so I fully expect that this has been completely rewritten and is now redundant at least 3 times, so.
Anyone else? Oh, sorry again.
What about VLAW encoding, like encoding instructions that overlap maybe?
I'm not entirely sure what you...
I mean, like for example, we have to encode a VLAW instruction, then maybe share some some fields.
I haven't looked at that kind of...
Okay.
So as far as I understand, it's not possible because it assumes a linear parser. At least as far as I understand, maybe someone else has the answer, but I think it assumes it's just a linear parser. So either you keep all these context within your classes, or you have to go, you can't just go back. So it might not be suitable for these. No one else? Well, thank you.